Okay, so today we're going to be learning about the Warshall's algorithm. The Warshall's algorithm is a systematic or an algorithmic way to compute for the transitive closure of a relation on a certain set. Now, why is this important? Now, the transitive closure of a certain relation on a certain set gives us many implications in different fields, such as graph theory, database management, social networks, NLP, and actually so much more. Now, given an adjacency matrix M sub R on a set A, where M sub R is equal to the following matrix, with the elements A, B, C. We choose a pivot K from the set A, where A has the following elements, lowercase a, b, and c. Usually, the pivot we choose is the first element on the set, which is A. This will keep our flow and our algorithm much easier to follow. Now, with our pivot K equal to A, we mark the rows and columns associated with A. That is the first column and the first row. Now, as we traverse our matrix, we mark all the zeros as red, and the current zero that we're working on, we mark as yellow. Now, how this works is actually with a general formula, wherein we have this certain formula with the source vertex, destination vertex, and the pivot, which is K. Also, by the way, not to be confused here is that this arrow does not mean an implication, but rather this denotes connectivity. Basically, what we're doing is essentially we're just checking if there's a connection from the source vertex to the pivot and the pivot with the destination vertex. Now, this sort of is derived from the concept of transitivity, wherein if A and B are in the relation and B and C are in the relation, then it implies that A and C are in the relation. Now, we apply the same concept in the Warshall's algorithm, but in reverse. But in this case, what we're doing is essentially we're iterating through the different zeros in the matrix, and we're trying to connect it with the pivot in such a way that in the end, we get our transitive closure. The first zero that we will work on is the one at row 1, column 2. That's the connection from A to B. Our source vertex here would be A, and our destination vertex here would be B. If you do not know how to work with adjacency matrices, basically, the labels for the rows here are essentially your source vertices, and the labels for the columns would be your destination vertices. In this case, for our first zero at A to B, our source vertex would be A, and our destination vertex would be B. Now, in that case, since our pivot is A, we simply substitute to the formula and we get the following. Since our K is A, it transformed as follows. Now, the connection from A to A exists, so A is related to A. And since in the matrix, we see that our source vertex A is connected to the destination vertex A because there is a 1 corresponding in the matrix. With that, the value for A to A would be 1, and A to B, since there exists no connection, it would be 0. And remember, with Boolean algebra, 1 and 0 is basically just 0. For our second 0, it would be at B to A. And this is marked by the source vertex of B and the destination vertex A. And currently, it is at 0. So we check if we can make this a 1 by checking with the pivot. In this case, we simply substitute B to A and A to A. And we see that 0 and 1 corresponds to a 0. So it remains unchanged. For our third 0, that would be on B to C with our pivot again as A. So B to A and A to C, we see that B to A is actually 0 and A to C is a 1, And 0 and 1 is actually just 0, so we still get a 0. And for our last 0, that would be at C to C. So we substitute for our pivot, that would be A, and we check for disconnection. On C to A, we have a 1, and on A to C, we have a 1. So we get a 1 and 1. And by the principle of Boolean algebra, we get 1. So we change our matrix from 0 to 1. Now, it is important to note that as we progress with our algorithm, we're actually changing the matrix itself. Now that we're done with the pivot A, we proceed with our new pivot, which would be B. So our K would now be equal to B. Now we follow the same approach wherein we traverse our whole matrix with our pivot. So our first 0 in this case would be A to B. And we simply substitute for K, and now in this case it would be A to B and B to B. We check for connections. We see that it would be 0 and 1. 0 and 1 is just 0. And from here, I will let the algorithm proceed by itself. Feel free to pause the video and try it on your own. Now that we've been able to select all possible pivots, and that we've used them each, we finally have our transitive closure.